Hello everybody and welcome back. So today we'll be talking about some of the applications to Bernoulli's equation, the equation that we saw in the previous class. And it turns out that this actually has a lot of interesting phenomena related with it. It can explain things as to why an aeroplane actually stays there in the sky instead of just falling straight down, or why a ball when thrown in air that is and it's spinning, why it seems to have an apparent lift, which you might know as the Magnus effect. So before we actually begin explaining the phenomena, let's have a short recap of what the equation is. So let me just state it over here again. So the equation simply stated is the sum of the pressure plus kinetic energy per unit volume, that will be rho v square by 2, plus potential energy per unit volume is a constant. So this means that we can write, generally speaking, for say a fluid at 2 points, we can give a subscript, say P1 plus rho V1 square by 2 plus rho GH1 is equal to P2, say the position of the fluid at some other point, to say P2 plus rho V2 square by 2 plus rho GH2, and so on and so forth. So in the first case, what we're going to have is we're going to come upon an interesting result which actually sort of verifies another thing that we saw earlier. So I'm going to assume that the velocity of the fluid is 0 at all points. That means the kinetic energy per unit volume is 0. So this term will just vanish, right? So suppose I have a container over here and it's filled with a fluid, right? And I'm going to consider, say, I'm going to let this be 0.1 and I'm going to let this be 0.2. So this, let this be height be h1, and I'll let this height be h2. Alright, so now what our equation tells us is we can equate the energy of the fluid at 0.1 and 0.2. That is basically Bernoulli's equation. So we can say P1 plus rho V1 square by 2 is going to be 0. So we can say rho GH1 is equal to P2 plus rho GH2. And if you're observant, you might have already noticed that this is nothing but Pascal's law. That is, the difference in pressure between any two points in a fluid is nothing but the density of the fluid times the acceleration due to gravity times the difference in the height between them. So I thought this is something that is pretty interesting and something that I should begin this video with. Sort of just like a verification of the fact that Pascal's law really is true and it does hold true. Alright, so that is the first result of sorts. Alright, so in this case over here we assume that the kinetic energy was 0 and that the fluid was static. So one of the limitations of Pascal's law is that it only holds in the case that fluids are not moving, that the fluid molecules over here are not moving. But what if the fluid is moving? That is, what if we have a pipe over here, right? And this pipe fluid is continuously moving. Well, we do have a pretty neat equation for this result as well. That is the equation of continuity. That is, if the cross section is A1 over here and A2 over here, we can say that A1 V1 is equal to A2 V2, where V1 is the velocity of the fluid at this point and V2 is the velocity of the fluid at that point. So that is one interesting equation. However, we can try and apply our Bernoulli's equation in this situation as well. And what we'll get is, so I'll assume that this fluid is at a height h1, right? And this fluid is at a height h2. And in this special case, and this is the ground, alright? And in this special case, I'm going to assume that h1 is equal to h2. So when I simplify the equation, I can write P1 plus rho V1 square by 2 is equal to P2 plus rho V2 square by 2, and I'm not writing rho GH1 because they get cancelled. So this again is a sort of if you qualitatively analyze this result, what it basically means is if the I'm just going to make it evident that there is some fluid over here. If we just say that suppose the pressure at this point over here is less and the pressure at this point over here is more, then the kinetic energy at this point has to be greater in order to sort of balance this equation right over here, right? Suppose if I just take this to the other side, suppose I say P2 minus P1 is positive, that is P2 minus P1 is greater than 0. We know that this is equal to rho by 2 into V2, was it V1 square? I think, yeah, V1 square minus V2 square. What this implies is that if this thing is positive, this thing has to be positive as well. So this means that V1 has to be greater than V2. So as a general statement, when the heights are the same, if the pressure is lower, the velocity has to be higher, and if the pressure is higher, the velocity has to be lower. So this general fact holds true whenever the heights that you're comparing the two fluid points are the same. So that is, well, yet another interesting outcome. Alright, so before moving on to the next application, let's recall a result that we got in kinematics. That is, if an object is allowed to fall freely under the influence of gravity through a height edge, what would be its velocity when it has crossed that height edge? Yeah. So let's imagine that this is the object and this is the height. Since it is under a constant acceleration, that is equal to g, we can apply the third equation of motion. So that would be equal to, say, and I'm assuming that it is allowed to fall freely from rest. So we can say v square minus u would be 0. So v square is equal to 2gh, right? So we find that v would be equal to root of 2gh, that is the velocity of a body that has fallen freely under the influence of gravity through a height edge. So keeping this result in mind, we'll derive a completely different velocity, but you'll find that these two velocities will actually be equal, or speeds if you want. And it's worth thinking about what it actually means, and that's something that I'll let you to ponder upon. So let's now look at a tank, alright? This is a tank, and I'll erase it over here because I want to draw a small orifice, that is a hole near the bottom of the tank. So this is going to be that hole, and the area of these area of cross section of this hole can be considered to be negligible. That is, if the area of the cross section over here at this point at the top of the tank is suppose A1, alright, and area of cross section at this point is suppose, it's not a length, I'm just going to let it be A2. Over there also it's not a length, so it's kind of misleading if I show it like that. If I let this be A2 and if I let this be A1, I can say that since A2 is very small and A2 is also quite large, I can say that A2 by A1 is approximately equal to 0. Alright, so when we use our equation of continuity, that is the velocity of at this and this point, you don't actually know what the velocity V2 is. However, and if I let this be V1, however, if we apply the equation of continuity, we can say A1 V1 is equal to A2 V2, right? So if I find A2 by V1 by V2, I'll find that it will be equal to A2 by A1, and we already know that A2 by A1 is approximately equal to 0. So we can also say that V1 by V2 is approximately equal to 0, and since V2 is some finite quantity and that is not, it's not infinitely large, we can say that V1 has to be approximately equal to 0. So using this information, we're going to apply Bernoulli's equation to the general case at this point 1 and this point 2, and we're going to find an interesting result. So if I find the pressure at these 2 points, these are both open to the atmosphere, right? So pressure at these 2 points is going to be equal to 0. I mean, it's going to be equal to the atmospheric pressure, not 0, my bad. So we can say PA plus, and I'm going to assume that there is a difference in height, say h between these 2 points. So this is the height, difference in heights between these 2 points, that is h. So I can, instead of writing rho g h2 and rho g h1 on both sides, I can simply write one term over here to account for both the heights, and that's rho g h1, that's the difference in heights between the 2 points, plus rho v1 square by 2. However, we just saw that v1 is approximately equal to 0, so we can neglect that term and I'll just remove that, and I'll say that this is equal to PA again, because as just said that this is again equal to the atmospheric pressure, plus over here, however, since we already accounted for the height, I'm not going to write the rho gh term. Instead, what the term that's going to be over here is going to be the rho v2 square by 2 term. So if I write that over here, rho v2 square by 2 is the whole equation over here. So I can cut the p and p on the both sides, then I can cut rho, and I'll find that v2 is also equal to root of 2gh. This is what is known as Torricelli's equation, and is the velocity of a fluid particle that has been kept under a height h of fluid particles. And well, I mean, you get the gist of what it means, right? So, and it's really surprising to see that these two values are actually equal. That is, it doesn't matter whether it's falling freely through air or whether there's fluid particles between them, the velocity is going to be the same. And that's something that really gives you something to ponder about and think about, yeah? Alright, so the next thing to talk about is the Magnus effect. That is, the lift that a spinning ball experiences when it is thrown through air. And I emphasize on spinning because a non-spinning ball, that is a ball does not spin, will not experience the Magnus effect. So before we actually analyze the case of the spinning ball, let's analyze the case of the non-spinning ball. So suppose we have a sphere and I'm going to use this shape feature over here because if I were to draw a sphere it would be completely horrible. So, and there are going to be air molecules all around it, yeah? And again, these are fluids. Fluids don't have to be, strictly speaking, liquids. Fluids are anything that can flow, and this includes both fluids and liquids and gases. So this is an air molecule, and the ball over here is moving at the speed of its center of mass, that is equal to, say, v center of mass, and it's not spinning. So you can say that the velocity of the air with respect to this sphere over here is going to be in this direction, yeah, because we're going to assume that the ball is moving faster than the air molecules are moving in this direction. So the velocity say at this point of the air molecules is simply going to be equal to v, is going to be equal to, say, v relative is going to be equal to v air minus v center of mass. So we can say that the air molecules are moving in this direction over here, and they're also moving at the same speed, because remember, this ball is not rotating, it's simply moving. So they'll be moving with the same speed in both cases. So when we apply the Bernoulli's equation, neglecting the difference in heights because the ball is very small, we're going to assume it's a point mass. That is, so that the difference in heights between these 2 points is almost negligible, so that we only have to rely on comparing the velocities and pressures. So like I said, like we talked about the general principle in this case, that is, whenever pressure is greater, the velocity is lower and vice versa. But since the pressures are equal, since the velocities are equal, the pressure difference between these 2 points, that is zero. That is, the pressures are equal. So suppose the net pressure exerted like this and net pressure exerted like this. The pressure exerted like this and like this balance each other, and the net pressure exerted on the ball is zero. So that was the first case. So now we'll move on to the case with the spinning ball. So let me just draw another sphere over here, and this is going to be that sphere. And again, let me draw my air molecules, if they can be called that. Alright, so what I'm going to assume is that this sphere over here is moving with an angular velocity omega in this direction. Alright. So the difference that this causes is that we are going to assume that the surface of the ball is rough. Alright. So what happens is that the air molecules at this point, they are already moving at some velocity v air, right? What's going to happen is that since the ball is moving in this direction, the ball is going to drag the air along with it. It's going to try and increase the velocity of the air so that the velocity at these 2 points matches. It's going to exert friction on it. So what happens is v net becomes v air plus some additional v drag. Alright, we don't care what that is, I'm just sort of highlighting it. We don't actually know what these numerical values are. Similarly, at this point, since it's moving in this direction over here, what happens is the velocity of air already has this velocity in this direction, but the velocity of the ball in this case is in this direction. So it's going to try and reduce the velocity of the air. So at this point, I'm going to let this point be v net up, and below it is going to be v net down. So what actually happens is V net down is going to be equal to V air minus some arbitrary V drag. We don't know what that is. The only reason I'm actually highlighting this is because I want you to know that V net at this point is going to be greater than the velocity at the bottom. So just knowing this fact, you already see where we are heading, because because of the general rule that is stated over here, which states that whenever the velocity is greater, the pressure is lower, right? So just to make that a bit clearer, let me write the equation again. P upper plus rho V net, say rho V net U, the whole square by 2 is equal to P down plus rho V net square down by 2. Now we know that rho V net up square minus rho V net down square will be positive, because V net up is greater than V net 2. So I can safely say that PD, because if I take it to this side and if I bring P to the other side, I can say PD minus PU is greater than 0, which means that PD is greater than PU. And the pressure just manifests itself in the form of force, right? So if suppose there's some area of cross section over here, I can also say that FD is greater than FU. And the net result of this is that instead of following this parabolic path, it gets a net upward force. That is, instead of having an acceleration of G, of constant acceleration of G downwards, it gets a net upward force, which causes it to have a slightly wonky parabolic trajectory, causing it to, say, suppose, get a slightly greater force upwards. So it gets sort of a lift. Suppose it's moving like this, and at this point it sort of starts to experience that force, right? So it will be somewhat like this, and then it will somewhat go like that. So instead of following the straight parabolic path, it will get a net upward force, and it will follow somewhat like this. Actually, I'm not sure if it does do it like that. You can probably find a few simulations online. And so cricketers actually make use of this when they're trying to spin their balls. They'll sort of impart it a spin, and that causes it to get a lift, and which is very useful when you're trying to get the batsman out. So that was another application. And the last one is actually how aircrafts actually stay in the sky, right? So this is actually based on the same principle as this, but in this case there are no spinning balls. The actual mechanism of how the difference in velocity is created is actually more of an engineering problem. Alright, so I've got a random stock photo from the internet for the purposes of illustrating the last example. So like we saw in the previous case, we need a pressure difference between these 2 points for there to be a lift, yeah? But in this case, the aeroplane is not spinning. Normally an aeroplane just prefers to move straight through the sky. It doesn't like spinning, yeah? So what we're going to, and so the actual details of how there's a difference in velocity created is more of a matter of an engineering. That's not something that I'd like to talk about right here, and you can probably read some Wikipedia articles to actually see how the difference in velocity is created. It's got to do something with the tilt of the wing, and I'm not too sure about that either. So here we're going to analyze the exact difference in velocity required for the airplane to stay in the sky. So we are going to assume that there's going to be a pressure down over here, and there's going to be a pressure up over here. And we know for a fact that pressure down minus pressure up, and again we're going to assume that the difference in heights between these two are approximately 0 to sort of make our calculations a bit easier. So we're going to say PD minus PU is equal to half rho into, say, and the velocity at this point is going to be higher, right? So we can say V up square minus V down square. Alright, and however we're not interested in the actual pressure, because that's sort of a difficult thing to calculate. Instead, because we don't actually know the net pressure that we need at each point. What is much more easier to calculate is the net force, because we know that it has to the minimum force required has to be equal to the weight of the aeroplane. If the pressure down is greater, then it will start going up, and if the pressure up is lower, I mean if pressure up is greater, then it will start going down. So the minimum weight has to be equal to the minimum force has to be equal to the weight of the aeroplane. So if I multiply this by A, I'll find that suppose the area of cross section that of the plane over here, I can say that half rho times A, because I can just take care of that, rho A into Vu square minus Vd square is equal to mg. And so solving this equation, you'll probably find the difference in velocities that you need by numerically inputting the values. You'll probably find the difference in velocity that you require, and an engineer will probably find a way to make that work. So I believe this will be pretty much it for this video. The next video that I'm thinking of making is somewhat ambitious, so it might be a bit longer than the time it takes for me to upload my videos, so do watch out for that. And I think that'll be pretty much it, and thank you for watching.